Okay, we learned from a previous segment that we can make expressions for simple harmonic motion in terms of displacement, in terms of velocity, and in terms of acceleration. And we can also correlate that to their maximum values over here. Now, in this video, we're going to look at specifically the case of a mass on a spring, and that mass on a spring can oscillate to and from two different maximums. So it can displace in the up direction and also in the down direction if you compress it or if you stretch it. So both of these amounts should be a value x from the equilibrium line. Now, if we apply Hooke's law, which recall Hooke's law is the force for restoration in a spring is equal to negative k times x, x being the displacement from equilibrium. And then, of course, for this situation, that would be a net force from the spring. So that's going to be equal to m times a according to Newton's second law. And if we take our previously calculated expression for a, which would be negative omega squared x, and plug that in, we get an expression that says negative kx is equal to m times negative omega squared x. So you've got x's on both sides. You have a minus sign on both sides, so none of that matters. And now you have an expression for k, and that comes out to be k is equal to m omega squared. We can also rewrite that in terms of omega. If we did a little bit of algebra there, we can say omega is equal to the square root of k over m. So what's the significance of this? Well, the significance of that is we can take that back into our original equations. So let's take the blue equation up top, for example. So we can have an expression for x sub t of a spring system. It's going to be a sine. And here's where it gets substituted. Instead of omega, you've got the square root of k over m plus whatever phase shift. So that's where it comes in handy. And it can be substituted for omega also for any of these, and also for your acceleration equation, or your energy equation as well. So let's see what happens when we start applying that. So remember, our new concept is that omega is the square root of k over m. That actually also leads us, since omega is equal to 2 pi divided by f, we could say that period would be the inverse of frequency, or the reciprocal of frequency. So period is going to be 2 pi square root of m over k, and frequency can be expressed as the reciprocal of that. So the square root of k over m times 1 over 2 pi. So we have these new expressions. Okay, so we look at this problem and we're asked to analyze this spring system. We've got two springs here, both with spring constant k, oscillating a mass m up and down. And we're asked to find the frequency of vibration. Well, now that we've done all that algebra, the work really is done. So you're going to have a frequency of square root of k over m divided by 2 pi. The only difference here is that you have two different springs, each of them with the value k, so you're going to substitute 2k. So 2k over m divided by 2 pi, and that's your expression for frequency. Let's try another one. Okay, so we have a 755 gram mass on a horizontal spring of constant 124 Newton meters, struck by a hammer, giving it an initial speed of 2.96 meters per second. Determine the period and frequency of the motion and the amplitude and the maximum acceleration. All right, we got our work cut out for us. First, let's draw a picture. So a hammer comes in, hits the mass, sends it in oscillation back and forth. We want to know the period and the frequency, and then we'll start there. So we have an expression for period, and period is just going 2 pi times the square root of m over k. Now in this case we have m and we have k, and we can plug in those values. So when we plug in 2 pi times the square root of 0.755 kilograms divided by 124 newtons per meter, we should get 0.49 seconds for period. Now once you have the period, frequency is just the reciprocal of that. So 1 divided by 0.49 seconds should give you a frequency of about 2.04 hertz, or cycles per second. Now question B, let's switch to the color blue, since they start with the same letter, B in blue. That's why. The question B asks for the amplitude of the oscillation. Well, if we want to know the amplitude of the oscillation, we have to think of the case in which all of this kinetic energy has converted into elastic potential energy. So we'll take the maximum kinetic energy, which would be at the very beginning when it first is hit with a hammer, and we'll set that equal to the maximum elastic potential energy. So then it will be 1/2 Ka for amplitude, which is substituted for the x maximum squared. So then algebraically we can solve for A here. First of all, the 1/2s go away, and then we can divide both sides by K. We can have mv max squared over K is equal to A. Should be A squared. So A is the square root that amount. So when you plug in your values for each mv max squared and K, you take the square root, we should get a value of 0.231 meters.